Hello, this is the first in our lectures on tensor calculus. This is a very big subject. It's hard to know where to jump into it, so I'm going to start with appearances. I'm going to imagine that there's some physical processes going on, and there's a single individual named Fred who's going to be doing all of the measuring for us. In everyday life, the speed of light is so big compared to typical distance over times that we humans deal with that people at one time thought that it was instantaneous. About 1676, the astronomer Romer showed by studying the eclipses of the moons of Jupiter that that's not the case. Romer managed to get a figure for the speed of light that's within 25% or so of the currently accepted value. Considering he had only very simple tools to work with, that's pretty good. According to our current understanding, light moves at about 3 times 10 to the 8 meters per second, or about 186,000 miles per second. I'm going to over-exaggerate some things that ordinarily we don't observe. I want to think about the situation where the speed of light is more human-friendly. Let's suppose that the speed of light, for instance, was only 1 meter per second. It's going to turn out that if that were actually true, the entire way that we perceive the world around us would be different. But in the meantime, I want to draw some silly pictures and draw some silly conclusions to start with today. I'm going to imagine that I have some particular individual person named Fred who is located in a flat plane, having previously set up the usual kind of Cartesian coordinate system. I'll say that Fred is located at x equals 5, y equals 7. Everything that Fred sees with his eyes is caused by light striking the retina at the back of his eye. So light must travel from some place to Fred in order for Fred to see that thing. I want to imagine that someone very quickly slaps down a metal bar that's 1 meter long, with one end at the origin, the other end on the x-axis at x equals 1. What does Fred see? For a while, nothing. Having slapped this metal rod into place, light has to be reflected from this point, travel to Fred's location, before Fred will perceive the right end of this rod. Assuming that the speed of light is 1, we can figure out how much time that's going to take. Since we're in a Euclidean plane, I can use the usual distance formula, which you remember comes from the Pythagorean theorem, which is valid within a flat plane, to calculate the distance. Divide that by the speed, which in this case is 1. Fred is not going to see that part of the metal rod until radical 65 seconds after the rod was quickly put into place. This is kind of strange. We put this object in place, but for a while, over 8 seconds, Fred doesn't see it. But it gets stranger. In this initial situation, this point is the closest point of the metal bar to Fred. All other points are further away. Being further away, it's going to take more time for light to travel from this point to Fred than it does to travel from this point to Fred. At the very end of this thought process, enough time will have passed so that light will have had time to travel from this point to Fred's eyes. How much time is that going to take? Doing the same kind of calculation as before, we found out that it's going to take square root of 74 seconds after the rod has been put in place before Fred sees this. This means that when Fred looks at this rod, he thinks it's just an ordinary metal rod and it's just sitting there, but there's more to it than that. Fred is seeing this end of the metal rod at a certain time. He's seeing this at an earlier time because it's going to take more time to travel to his eyes. He's seeing this further back in history than he is seeing this. Fred doesn't know it, but when he's looking at that metal bar, he's looking at a big, messed up mixture of time coordinates. Luckily, it doesn't matter because the metal bar is not moving or anything. So to summarize, Fred gets into position. We slap this metal bar down very quickly. After a while, Fred sees only that, and then pretty soon he sees other points, and then after square root of 74 seconds, he sees the entire thing. Fred is going to think, if he doesn't know any better, that bits and pieces of this metal bar are assembling themselves out of nothing, like a magic trick. In reality, of course, nothing like that is going on. It gets worse. Imagine now that not only has someone quickly slapped the metal bar into place, but they've also given it a speed of 0.9 in the positive x direction. What does Fred see? Initially, nothing. Because light hasn't had time to travel from here to Fred's eye. Once again, you could figure out how much time that's going to take, but that's not what I want to focus in on. At a different time, Fred is going to observe the point at x equal 1/2 to begin moving. He's already seeing that this has moved off to the right. After a while, Fred is going to perceive that those points have not moved any, but the other points have. What Fred is going to perceive is that the metal bar is longer than 1 unit by subtracting the ending x coordinate and the starting x coordinate. After square root of 74 seconds, Fred sees with his eyes that this point is now moving as well, but the other end, according to Fred's perception, has moved out quite a bit past x equal 1. If I wanted to be facetious, I could try to claim that this is the well-known Lorentz expansion. Those of you who already know some relativity will know that I'm just joking there. The metal rod is 1 unit long. Fred's perception is incorrect. Having gotten worse, it now gets more worse. Assume that Fred, again, is at x equals 5, y equals 7, except this time I'm going to have a vertical metal rod lying along the y-axis. At least for a while, the closest point of this rod to Fred is this point, the point at the top. Fred will perceive with his eyes that point to begin moving before any other point moves. Very shortly afterwards, Fred will see this point moving, but lower down points not. this point moving, lower down, not. At least for a while, at the beginning of this situation, Fred is not even going to perceive that that metal rod lies along a straight line. Without doing some detailed calculations, I don't really know that these are straight. They could be curved, as in parabolas or something, but I do know they are not straight lines parallel to those straight lines. If I have a vertical metal bar moving to the right, Fred is going to perceive, at least at times, that the shape of the straight metal rod is that. As your first discussion exercise, think about having the square in the xy plane, where x can be anything from 0 to 1, as well as y, going from 0 to 1. This begins to move in the positive x direction at speed 0.9. What does Fred see? Is it going to be true that he's going to see a four-sided figure, the sides of which are always straight lines and form parallel pairs? Or is something much weirder going to happen? I'll post this as a question in the discussion section. This has all been kind of silly, though. It's not as silly as what I'm about to talk about. The last thing I want to talk about in my introductory comments seems even more silly than what I was talking about a minute ago. This is going to be called the "don't miss the bus" effect, and at first glance it seems ridiculous, but it's going to come back to bite us later on. Imagine you've got a bus. It's sitting on some conveniently placed number line. The left end of the bus is located at x equals 10. This is measured by some person or the other. Then, the right end of the bus, its location is going to be measured as well, but the person who does it took 25 minutes off for a coffee break. Since the bus isn't moving, it doesn't make any difference. The two people get together, they say, all right, the right end is at x equals 50, the left end is at x equals 10, 50 minus 10 is 40, the bus is 40 units of distance long. Later, another pair of people agree to do the same measurement. Their conclusion is that the bus is 800 feet long. When this is reported back to central authority, obviously this is not right. So they begin an investigation. The first person verifies that he measured the x-coordinate of the left end at x equals 10. The person who measures the right end swears up and down that the x-coordinate he measured was at x equals 410. Subtracting those two numbers, you get 400 units of distance. This is apparently contradictory until you ask that second person the details of what all was going on. So the first person measures the x-coordinate of the left end to be 10, and the second person went off and had a coffee break, came back and measured the x-coordinate of the right end. Unfortunately, the bus was rolling down the street, so this doesn't give me a good measure for how big the bus is. This is going to be the miss the bus effect. And you might be thinking that only a complete bozo would let that happen. We'll see. If I want to measure the length of a bus, it's important to find the coordinates of the beginning and end at the same time. It's a good thing that time is absolute and space is absolute, or we could easily get confused about that kind of thing. This obviously is foreshadowing. The punchline for right now, though, is this. If I want to get an idea of what's really going on in a given physical situation, a physics problem, it's not good enough to have one single individual with a telescope or a pair of binoculars or something. We saw that in the first silly example. The second one is, if somehow it wasn't true that time was absolute, the miss the bus problem would become an acute problem. It would cause us lots of trouble. We wouldn't be able to accurately calculate how long a bus is, for instance. This is going to be my segue into the idea of an inertial observer, which will be what we begin talking about in the next video. In the meantime, I hope that everybody has a good day, and I'll talk to you again soon.